We're about to take a look at how to use a BCA table to solve a complicated limiting reactant problem. The BCA stands for before, change, and after. And you can use this table to take a look at everything you have before a reaction takes place. The C stands for what changes through the course of the reaction, and A is what you have after the reaction is complete. An important thing about a BCA table is everything must be in moles, because that's how we count things in chemistry. So I've already started the BCA table. I rewrote the balanced equation at the top, and then on the left you'll see BCA. Those will be my rows for before, change, and after. What you'll want to do is plug in all the moles of everything you have before the reaction takes place. Now, of course, most problems don't give you moles to start with, so you need to take the grams that they provide you and convert to moles. I'll trust that you're able to do that conversion, and so go ahead and do your conversion on a separate piece of paper, and then when you have determined the number of moles you have before the reaction takes place, write it into the table. So for example, it says I have 75.3 grams of the copper 2 chloride. After I converted it, I learned that that would be equivalent to 0.56 moles. And then I did the same thing for the 106 grams of potassium iodide. I learned that I had 0.638 moles also. Everything on the right-hand side represents the products, and of course you don't have any of those to start the reaction. So before the reaction takes place, I'll put a 0 for all three products. Okay, now we're ready to look at the change that's going to take place. Of course, this reaction is going to run to the right. And this is where the numbers in red, the coefficients of the balanced equation, become important, because you're going to react in, say, a 2 to 4 ratio for the copper 2 chloride compared to the potassium iodide. So what we're going to use here are those numbers. We're going to say we'll lose the copper 2 chloride, and so I'm going to do a little subtraction. This is a vertical math problem. The change column is going to be a subtract, and I'm subtracting 2x. I don't know what x is, but some amount of that copper 2 chloride is going to go away. I'm going to use the 2 there, matching up with this 2 here, the coefficient. Okay, so if 2x of the copper 2 chloride is going away, you can probably guess here, we're going to see that you're going to have Ki go away at an amount of 4x, okay? Because the mole ratio is 2 to 4, so we need to keep that consistent with what happens in the reaction. Now over on the right-hand side, all of these products are going to be gained. So I'm going to put a plus sign for the copper 2 iodide, but I'll place a 2, and again, x. Okay, you can see the two copper compounds both had a 2 on them. The copper 2 chloride is minus 2x, and the copper 2 iodide over here on the right is plus 2x. The iodide here is plus, it's kind of an ugly looking one, but that's what that is. That's a 1x. And then your KCl, potassium iodide, plus 4x. All right, so we're just dropping down those coefficients and calling everything x. Once we figure out what x is, we'll be able to figure out how much of everything goes away, and for the products, we'll be able to see how much they form. What you're seeing here are vertical math problems. I sort of separated them by yellow lines so you could take a look at that. Okay, so now we're ready to look at what's going to be happening after the reaction takes place. So think about this is a series of 5 math problems, 5 vertical math problems. So after my copper 2 chloride, I should have 0.560 minus 2x. My Ki, I'll have 0.638 minus 4x. Copper 2 iodide is just a 2x. And my iodide is 1x. I'll just put an x there. And KCl is 4x. Okay, so I've just looked at each problem vertically. Now, if I could just figure out what x was, I would know what I had after for everything. I just have to figure out what x is. Well, figuring out x, this is kind of the tricky part. You have to look back at your two reactants, and if this is a limiting reactant problem, one of the two should be 0 when you're done with the reaction. And this takes a little bit of guess and check. You try to make an educated guess about which one you think is going to be limiting. Now, as I look at this, I can see that Ki, I'm going to need twice as much of it because of the 2 to 4 ratio. I'm looking again at the coefficients, 2 to 4, so I can see for Ki I need twice as much. So even though I have more Ki before than I have of the copper 2 chloride, I can see it's not twice as much. So I'm going to make an educated guess here that it's probably this Ki that's limiting. Now, if you did not see why I picked that, don't worry. You really can just pick either one of the reactants and call it limiting. If you choose the wrong one, you will get an X that doesn't make sense. You'll get a negative number, and then you'll know you chose poorly and erase your limiting reactant choice and choose the other one. All right, so I'm going with Ki being limiting. What that's telling me is that this after should be 0. That's the definition of a limiting reactant. It's all gone. Now I can solve for X. 0.638 minus 4X should be equal to 0. And that's a simple little algebra problem in which we can solve for X. And we'll learn that X is equal to 0.160. Okay, now that I know what X is, you can substitute it in for all of the other chemicals because it's the same. So over here, the tricky part of this problem is figuring out what the excess amount is. But now I have the answer. It's 0.560 minus 2x. X was 0.160. That brings me to 0.240 moles. So there's my excess copper 2 chloride. Also, if I wanted to learn how much product was formed, I could pick any one or all three of the products, in fact, and figure them out pretty quickly. The copper 2 iodide would be 2 times 0.6, so I'd have 0.32 moles of that when I'm done. Here, the question had asked how much iodide forms, or iodine rather, and X we've determined is 0.60, so I know that mole now. And lastly, I could say that KCl is going to be this many moles, 4 times 0.46, so 0.64. Okay, so the BCA summarizes everything in terms of moles. Again, I took a great educated guess. I circled the Ki to be limiting and called it 0. If I had chosen the other reactant to be limiting, I would have found my X to not make sense, and I would have wound up with negative numbers here afterwards. Of course, you can't make a negative amount of something or have a negative amount of something. So just go back and change your limiting reactant if you happen to make that error. The question asked how much excess reactant remains, so officially they didn't ask me for grams, so I could just answer this, that the excess CuCl2 is 0.240 mole. Of course, you all know how to convert that to grams if you needed to. They also wanted to know how many grams of iodine we're going to form, so I suppose we'll be thorough here and answer that. 0.160 moles of iodine is what they report, or what we found in the BCA table. You just have to wrap that up by changing it to grams. I have a molar mass of this, 253.8 in a mole of iodine. So that means we expect to produce 40.6 grams I2. That's our theoretical yield, our maximum we could make based on our calculations. Giving the limited reactant was, what was it, Ki. So there you have it. That is your BCA table. So just remember, everything's got to be in moles. And the other tip I have for you is make sure that when you do the change is where you deal with the coefficients. That's the only place that you're going to have to worry about coefficients is when you do that change part. You see the numbers there in red. That's the only time you have to worry about the coefficients. Hope this was helpful.